Today's webinar will be on the geology and mineralization potential of the Gerry Well Greenstone Belt, which is situated in the northeastern Yilgarn Craton. This study formed part of a collaborative research project between the Geological Survey of Western Australia and the China Geological Survey, which took place between 2017 and 2019. More details of this study can be found in the GSWA record shown on screen, which can be downloaded from the Demir's e-bookshop. The location of this study is the Gerry Well Greenstone Belt, otherwise known as the Collurabbie region, which is situated in the Burtville Terrane of the Yilgarn Craton. Here I have highlighted the Kalgoorlie Terrane in red, which hosts many types of mineral deposits including Komatiite-hosted nickel, orogenic gold, volcanogenic massive sulfides, and banded iron formations. Mineral exploration in the eastern goldfields has predominantly focused on this terrain, leaving the eastern terranes less explored and less understood. However, the Gerry Well Greenstone Belt has been explored for a number of years for both Komatiite-hosted nickel sulfides and orogenic gold mineralization. 8 drill holes spanning across the Greenstone Belt were selected for analysis for this study. The selected drill holes are confined to the western side of the Greenstone Belt, as there is limited diamond drilling elsewhere. The 2 northernmost holes in this study are EIS drill holes, while the others were kindly loaned to us by Regis Resources for sampling. Each drill hole was geologically and hyperspectrally logged and sampled for petrographical, geochemical, and geochronological analysis. Portable XRF measurements were taken every metre in ultramafic rocks and every 5 metres in non-ultramafic rocks or close to lithological contacts. The data is not used further in this study, but results can be found in the appendix of the record. All drill holes were run through GSWA's high logger at our core library in Carlisle. Results won't be discussed during this talk, but each drill hole has its own high logger record discussing results and interesting finds, which can be found in the Demir's e-bookshop. As geochronology and geochemical samples in this part of the world are fairly sparse, one sample for geochronological analysis was taken from drill hole RRLCRDD002, and 128 geochemical samples were taken across all 8 drill holes. Veins and xenoliths were excluded in samples where possible, and weathered material was removed prior to sample submission. This study was originally proposed as a nickel prospectivity study, so there was a large focus on the chemistry of ultramafic rocks. The geology of the Collurabbie region is poorly understood, as the Gerry Well Greenstone Belt is extensively covered by Cenozoic material. Lithostratigraphy has been inferred entirely from magnetic data and selected diamond drill core obtained from nickel exploration from close to the western margin of the Greenstone Belt. Stratigraphic relationships are rarely evident in drill holes and possibly only locally relevant. More regional stratigraphic and structural studies are required to establish more context. Detailed descriptions of lithological distributions can be found in the record. However, the main rock types across the 8 drill holes include ultramafic rocks, basalts, and various sedimentary rocks. There are also a large amount of undifferentiated metamorphic rocks, with protoliths often being quite hard to distinguish due to intense alteration and deformation. This is where portable XRF data and hyperspectral data was particularly useful, as chemical and mineralogical changes could be quickly and accurately identified. As said before, the study was originally proposed as a nickel prospectivity study, so naturally we're quite interested in the ultramafic rocks. In drill hole CXDD002 and 3, towards the northern part of the Greenstone Belt, ultramafic units are less than 15 metres thick and are completely altered to either talc carbonate or serpentine, with no primary textures preserved. In the 2 drill holes ending in 006 and 005, undifferentiated ultramafic rocks are strongly foliated and locally partially to almost completely overprinted by sporadically folded veining. Drill holes RRLCRDD002, 3, and 4 contain talc carbonate and serpentine altered ultramafic and komatiitic rocks, with textures sometimes being preserved. The core image and photomicrographs here are from drill hole RRLCRDD002, and were the best examples of primary cumulate and spinifex textures being preserved in the region. Before diving into the particulars of the nickel prospectivity of the Collurabbie region, I first want to explain prospectivity in terms of the bigger picture. A mineral system is a mass and energy flux event And in order for mineralization to occur, there needs to be some key critical ingredients taking place. These critical ingredients are a source of energy, metals, and transport, a transport pathway, a trap for mineralization, which is typically some sort of physical or chemical process, and lastly, all of that needs to be preserved through geological time. If any of these critical processes are missing, prospectivity for whatever mineral system you're looking for will be low. For komatiite-hosted nickel, these are the key critical processes that are needed in order to form a mineral deposit. The source of metal here is the komatiite magma itself, followed by transportation of said magma through the crust. It is commonly accepted that these magmas are erupted sulfur undersaturated, with crustal sulfur needing to be added to achieve said sulfur saturation. Once this saturation has occurred, metals from the komatiitic melt are able to sequester into sulfide liquids, which can then concentrate as sulfides. Preservation and modification of ore bodies then needs to be taken into consideration when exploring for these deposits. Lithogeochemistry has been widely used in the exploration for komatiite-hosted nickel deposits for a number of years. These two particular graphs, which show ultramafic samples from the Collurabbie region, use nickel, chrome, and titanium to help discriminate komatiite facies and rock types. When exploring for these deposits, mineralization is typically found in areas of thick cumulate rocks, as opposed to areas of spinifex textured rocks, which represent flow tops or flanking environments. As komatiites are typically altered and deformed, primary textures are often difficult to distinguish, so the use of nickel, chrome, and titanium, which are typically immobile during alteration, can help distinguish what our rock types are. In this particular case, the graph on the left shows nickel-chrome versus nickel-titanium ratios, and as you can see, a large majority of samples plot in the spinifex field, shown in green. They don't trend towards cumulate zones. The graph on the right plots nickel against chrome, which shows the same thing. A majority of samples plot in the spinifex field in the bottom left-hand corner with low nickel values, and trend upwards along the barren komatiite trend, as opposed to along the bottom mineralized komatiite trend. Enrichment and light rare earth elements and incompatible trace elements can be used to detect crustal contamination, which is of course important to help distinguish whether an external sulfur source has entered the system. On this particular plot, which shows rare earth elements, a downward trend from lanthanum to samarium indicates some form of crustal contamination has occurred, which here can only clearly be seen in 3 samples from the study. These 4 graphs showing incompatible trace elements also show limited evidence of crustal contamination, with very few samples trending in the direction of the crustal contamination arrows as shown on each plot. Coming back to the bigger picture and asking ourselves if all key critical processes for mineralization took place in the Collurabbie region, the source and pathway components were achieved. Komatiite magmatism occurred and there was obviously transport of said magma for us to be able to observe it in core. Unfortunately, when looking at lithogeochemistry, there appears to be a lack of strong crustal contamination signatures in these rocks. When observing drill core, there also appears to be a lack of suitable sedimentary rocks which could have been assimilated, and no physical evidence for komatiites assimilating other rock types. The ultramafic geochemistry and sporadically preserved primary magmatic textures also indicate that many of the komatiite rocks in the area were probably spinifex textured or flow top units, possibly from flanking environments. The cumulate facies rocks are also generally relatively nickel poor, the samples lying on the barren komatiite trend. So unfortunately, while the nickel story so far doesn't look particularly favourable, something else of interest that stemmed from looking at drill holes from this region was the presence of the rocks on screen, which are tonalitic in composition, contain several mafic dikes and enclaves, and contain quite a large amount of biotite clots after hornblende, which are very similar to sanukitoid rocks found in other areas of the eastern goldfields. So what is a sanukitoid? They are defined as a monzodioritic, dioritic to granodioritic intrusive rock, typically contain hornblende, and have high concentrations of chrome, nickel, large iron lithophile elements, and have a high magnesium number, so chemistry that you would typically expect to see more in mafic rocks. The table here shows chemistry of these rocks from the Collurabbie region compared to typical chemistry of sanukitoids. Unfortunately, due to the nature of these rocks, being that they are full of cross-cutting dikes and enclaves, we were only able to get 3 clean samples for geochemical analysis. Nonetheless, the chemistry we do have turns out to be quite interesting and suggests that chemically these rocks are most likely sanukitoids. While their silica content is high and trace element concentrations are lower than typical sanukitoids, trace element concentrations are still high for felsic rocks at this given silica content. We believe the reason behind the high silica content here reflects a high degree of fractionation within the rock. While we are unsure if these are in fact true sanukitoids, based on the chemistry and mineralogical factors, we have decided to call these rocks sanukitoid-like rocks, with comparison to related, less fractionated samples from the region needed to confirm their true identity. Dating of this sanukitoid-like unit, which is interpreted to be younger than Komatiites, has yielded a magmatic crystallization age of around 2713 million years. Full details of this analysis can be found in the reference on screen. What is curious to note is that similar ages in similar rock types have been found across the Yilgarn Craton. These include a dacite at Collurabbie, which has an age of 2708, a volcanogenic conglomerate at the Black Swan nickel deposit with an age of 2712, and rocks with an age of 2714 and 2719 in the LSHD6 drill hole in the Geologist Greenstone Belt, which is just to the south of the Gerry Well Greenstone Belt. No previous geochemistry has been done on the geochron sample from LSHD6. We couldn't find any detailed lithological information, so we accessed this drill hole and sampled it to see if it was comparable to the sanukitoid-like rocks at Collurabbie, given that the ages are so similar. This plot shows the geochemistry of various sanukitoid samples throughout the eastern Yilgarn. Circled here are samples from the Burtville Terrane. LSHD6 from the Geologist Greenstone Belt are in pink, and Collurabbie samples are in red. As you can see, both sets of samples have relatively higher silica content and lower trace element concentrations compared to the rest of the samples. Another point of interest here is the samples in yellow and orange, which are rocks with older ages from the Kalgoorlie Terrane from Collurabbie and Black Swan. These samples, on first glance, show more comparability to Burtville Terrane samples as opposed to the other samples. So this geochemistry, along with the correlation in geochronology, would suggest that there's a previously unrecognised hydrous magmatic event which has occurred in the Burtville Terrane. So what are the implications of such an event? It is widely acknowledged that there's a spatial and temporal correlation between gold mineralization and sanukitoids. Whether sanukitoids themselves are sources of gold is still not well understood. However, their emplacement and transport are believed to be controlled by large translithospheric structures. Structures of this nature are also important pathways for hydrothermal fluids that transport gold from the mantle or crust, so the fact that these rocks are in this region could have further implications for gold exploration. From a geochronological perspective, the 2713 age of sanukitoid-like rocks at Collurabbie is significant as it represents an older event of hydrous felsic magmatism in the region, particularly when compared to the sanukitoid rocks in the Kalgoorlie Terrane, which have been dated between 2.68 and 2.66 billion years. The sanukitoid event in the Kalgoorlie Terrane is very well linked to gold mineralization that occurs throughout that terrain. As we're seeing similar rocks with practically the same age occur in the Geologist Greenstone Belt, this suggests that this event could have been widespread across the Burtville Terrane. This, combined with the fact that rocks with similar chemistry and ages are being found in the Kalgoorlie Terrane, of course has wider implications from a regional geological point of view, but the full extent of that is currently unknown. Based on drill core relationships, the sanukitoid-like rocks sampled at Collurabbie intrude a sulfidic sedimentary rock that are broadly contemporaneous with Komatiites. This suggests that Komatiites were in place before 2713 and are therefore older than the highly mineralized Komatiites which occur in the Kalgoorlie Terrane. In summary, the main outcomes of this study is that based on geochemical and mineralogical characteristics of Komatiites, their prospectivity for major nickel sulfide mineralization appears to be comparatively low. In saying this, however, it is important to note that only 8 drill holes were sampled throughout this region, mostly because this is what was available at the time of sampling. Drill holes in this particular region were quite concentrated along the western margin of the Greenstone Belt, with no holes along the eastern rim. It is also important to note that although it appears as though a major critical process for mineralization was missing in the studied drill holes, there has been recent discoveries of nickel, copper, cobalt, PGE sulfide mineralization in this greenstone belt, which indicates that further work is required to understand the full metallogenic potential of nickel in this region. The recognition of the sanukitoid-like rocks in the area, both in the Collurabbie region and in the Duketon Greenstone Belt, suggests an older hydrous magmatic event in the Burtville Terrane. The clear link between hydrous magmatism and gold mineralization is well known, however the implications of this event in the Burtville Terrane is not fully understood as yet and requires further investigation. As sanukitoid-like rocks in the Collurabbie region are interpreted to be younger than Komatiites, Komatiites here represent an event older than the highly mineralized 2.7 billion year Komatiites in the Kalgoorlie Terrane. There are known older Komatiite ages in the eastern terranes of the eastern goldfields, for example Mount Indara and Mount Fisher, but what this means in terms of nickel prospectivity is still not fully understood. Thanks for listening to this webinar. As mentioned at the start of the talk, more details of this study can be found at GSWA record 2022/2. Thanks.